Welcome to Data Science with EJD. In this video, we move on to regression metrics. We've been using some of these metrics as we looked at different regression algorithms. But in this video, we zoom into the metrics in particular and see how they perform, uh, you on regression models. So the learning objective here is to use MAE, MSE, RMSE, and R squared to evaluate and compare the performance of multiple regression models through practical coding. So that's our objective here. Of course, you'll find out what all of these things mean. Of course, you've seen some of them before. I think MAE is about the newest I've introduced in this playlist so far. So here we take a deep dive into this. So again, of course, we're talking about regression metrics, and we know that under machine learning, there are three basic types of learning. We have supervised learning, unsupervised learning, and reinforcement learning. And all along, we've been x-raying supervised learning, where we saw that supervised learning is categorized broadly into classification and regression. So we've looked at the classification algorithms like decision tree, random forest. Of course, in the last videos, I looked at decision trees and random forest also for regression in that context. And of course, we saw things like k-nearest neighbor. So here we're talking about regression. So when you use regression algorithms, there are some metrics that we use in seeing how well the models perform. So core regression metrics, to measure how well a regression model performs, we use error-based and goodness of fit metrics. Error-based and goodness of fit metrics, like the ones outlined already. The first metric is the MAE, which is the mean absolute error. Just like the name implies, we get the absolute errors. Absolute is just want to take the magnitude. You don't care about the sign. So we take the sum up all the absolute errors and find their average. That's what mean absolute error is about. So that's average absolute difference between actual and predicted values. So MA is 1 over n, summation from I equals 1 to n of yi minus yi cap. So yi is the actual value, while yi cap is the predicted value. So you find that difference, whether it's positive or negative, you don't care. That's why it's absolute. And then you sum up all of that and divide by n. That's why it's mean absolute error. And the range is between 0 and infinity. So it can take any value from 0 to infinity. So that means that in that case, the lower the value of the mean as absolute error, the better, right? Then you also have mean squared error. Mean squared error, of course, we've been using that a lot. So it is average squared difference, and this penalizes large error. So you have, instead of absolute value here, you have the square of the two. So it's mean squared error, right? So you divide by n. Again, because the range is from 0 to infinity, so the smaller the MSE of a model, the better the performance of the model. Then we also have the root mean square error. So just like the name implies, it is the square root of the mean squared error. So it is interpretable in original unit. So this is more interpretable than MSE itself. And of course, because it lies between 0 to infinity, the lower, the better also. Then you have R squared error, which is proportional of variance in the target explained proportion of variance in the target explained by the model, and it is calculated by R squared equals 1 minus SS residual over SS total. That's sum of squares residual and sum of squares total. And interestingly, this one is between minus infinity to 1. So this simply means that the closer to 1, the R squared is the better. So for these first three, this lower the better, but for R squared, the higher the better. Of course, it is capped at 1. So the closer to 1, the R squared score of a model is the better for you. So you can actually interpret these models having this understanding. So let's look at a step-by-step coding workflow. Of course, the first thing, as usual, is to import the necessary libraries like NumPy, Pandas, NumPy for numerical computations, Pandas for data analysis, data manipulation, data cleaning, and things like that. And of course, the rest, you have scikit-learn for getting the data sets. We'll be using the California housing data set a lot. Then train test split, you need that. Then here we are talking about different metrics, right? So we are using, so we want to test it across different models. So we have linear regression, reach. For tree, we are also using decision tree regressor. We are using random forest regressor also. Then we need the metrics like mean absolute error, mean squared error, R squared, score, like that. Then we have of course, we need matplotlib and seaborn for visualization. And don't forget to run. So it's only run if you have a number here. So it means it's been run. For this one that is blank, now it means you have not run it. So The next thing we want to do is to load and prepare the data set. So since we're using the California housing data set, so it's more like we want to predict the mean value of the housing based on some features, right? So we have X, Y. So we have data.data. That's for the features, and data.target. That's for the target, which is the housing value. So the data it has been already structured in such a way that this okay, I keep forgetting to put line numbers for easier referencing. So the data has already been prepared in scikit-learn in such a way that calling data.data just gives you the features, while data.target gives you the target, which is the price. You want to predict housing price. Then, of course, training split into training and test sets. So you train, you divide the data set you have. A portion of it, a larger portion of it goes to train the model, while by the time the model has been trained, you now try to verify if the training was good enough. Like then you test. So this is always standard. You see, we use this every time for every model. So X train, X test, Y train, Y test, train test split. So you have X, you have Y, then the test size is 0.2. This can vary, right? The most popular, it can be, you can use 20%. 0.2 means 20% to test, 80% to train. So you train with 80% and now test with 20% and see how well that performance looks like. So sometimes you can have test size to be 0.3, depending on the kind of data you basically have, right? And then this random state is to ensure that when you run the data, when you run the code several times, the values don't change. So that's to make sure you always get the same value. And of course, one thing I've always encouraged is if you're learning, if you are doing this right, you have access to all my materials. So in fact, usually the first thing you should do is download all the materials and follow along step by step. Now, when you see a number like this, you can change the number to see what happens, or you can delete something to see if you delete it, what happens. So that way, by the time you internalize all those changes, you can know what exactly each aspect of this thing is about, what each aspect of this thing is actually about. So step three, you want to define the models now. So all the models we've seen so far, we've seen linear regression, we've seen ridge regression, we've seen decision tree, we've seen random forest, you know. So you just call all of them linear regression, ridge. For ridge now, you need a lambda, right? You need the penalty term, which presses. Now, the only thing we are not using here is lasso, but we know generally that lasso, depending on what you want, right? Lasso is very good for feature selection because it compresses the coefficient of some variables to zero, so that you can now know that those are not really important. So here we have not used lasso. So for ridge and lasso, we need lambda, which is the penalty term, which penalizes the system to get something as good as possible. So you have decision tree and random forest. So here, of course, random state 42 is needed for random forest and decision tree. And of course, since random forest is aggregation of trees, so n estimators means you have 100 trees, right? You're putting them together because it's an ensemble method gathering trees together to form a forest. Okay, then we go to define the evaluation function. So define evaluation model, name, model. So you're using a Python function called evaluate model, and it takes the name, the model, the train, the test, X train, X test, Y train, Y test, right? And then it fits them. It fits each model to the train and to the train data, and then it makes prediction. Model to predict X underscore test, all right, and then we do the evaluation. So minimum absolute error, y test, y pred, MSE, mean squared error, y test, y pred. Of course, RMSE is square root of MSE, so that's why you need numpy. So that's np.sqrt. Sqrt is a function inside of numpy library of the MSE. Then R2 score is R2 underscore score, y test, y pred. Of course, all these are downloaded from scikit-learn, as you can see. So a scikit-learn.metrics, that's where we get all those things from. So you can see root mean squared error is not here because it is just the square root of mean squared error, which can be obtained using numpy. So with this now, you now want to return the model, that's the name of the model, the MAE value, the MSE value, the RMSE, and R square value, right? So now that has been run. So the next thing you want to do is you want to evaluate all models now. So of course, to call the model, of course, you need the evaluate model name, right? So evaluate model. So you have the result. This is an initialization. So you now say for name model in models dot items. So each item here, you know, each item of these models, like right here now, for each item of this now. So you append so result.append evaluate model using the name, the model, and all that. So you're iterating over them to get the values, and then you get the result as a data frame. So you have pd dot data frame. So whatever result you get from here, you put it right here so they can have it as a data frame. So result df dot sort value. So you're sorting values by r squared in ascending order in place true. So result df you have it as a data frame. Okay, I think there's something I did. Is there something I did not run? What's happening? X train is not defined. What's that? X train is not defined. X train is not defined. Why is that? Let me see. X train is not defined. Ah, I didn't run this. Yeah, you see that that problem can easily occur. So I didn't run this. That's why we have that issue. Now it's gonna work perfectly. Okay. Then we come here and we have this. Yes. So now it works good. So it's still running. Still running. Takes a bit of time because I'm iterating over each of the models and it's evaluating, it's fitting the model, okay, the model has been fit, so it's evaluating each model. So now the result is out. All right. So, and we have arranged according to R square. So the one with the biggest R square comes as expected. Random forest is always boss. So that's 0.8 followed by decision tree 0.62. Ridge regression is next in line with very close to this, except that it is a bit better than linear regression, and linear regression is last, right? So of course, if you look at other metrics, they will also follow like that because for these other metrics, the lower the better, right? So random forest is the lowest compared to the rest also for each of these other metrics, right? So random forest is boss as usual. So visualize the results. So you want to see how each of these perform. So you have the regression metrics for multiple models. So you have a bar plot. So here the data is result underscore df. That's the data frame. Melt id versus model. So x is model, y is value, and here is according to the variables. So you do this and you get this. So you can already see this is r squared. So obviously the tallest r squared tells you the best model. So going by r squared, um, random forest is the best, right? Followed by ridge regression. No, followed by decision tree, followed by ridge regression, and followed by linear regression. Then going by MSC, that's the something that looks like orange like this, or is it peach like that this is called, I don't know, or brown, so to speak. So for in this case, for every other time, the shortest the better. So for random forest, MSC is shortest, so it just goes like that. Same for RMSE, the green, so the shorter the better. And lastly, R squared. Okay, we've done R squared. MAE, the shorter the better. So obviously, random forest is boss. So the insights we have here is that the best performer is random forest because it has lowest mean absolute error, median mean squared error, and root mean squared error, and the highest R squared. Obviously, the overfitting risk decision tree may overfit, shown by lower R squared. All right. And the baseline is that linear regression can serve as a good baseline. So linear regression is the starting point when you talk about regressions, right? Then summary and best practices. Use multiple metrics for a more complete performance picture. So if you are working on a real project, so you want to use all the possible metrics you can use so that you can now see of course, as you know how to read the metrics now, the higher the closer the R squared is to one, the better, and the lower every other metric is, the better. All right. So use MA when outliers are not critical. Use MSE and RMSE when penalizing large errors is important. Then use R squared to understand the proportion of variance explained. Now, if you're in doubt, use everything and just read. Just look at the readings. So for comparison, use cross validation for robustness, not shown here but recommended. So cross validation is another thing you may want to consider if you are really interested in robustness. Then the possible ways to extend is to add cross validation using cross val score or grid search CV. Evaluate on custom data sets or with feature engineering. Track training time and prediction time for performance benchmarking. So you want to know which model runs faster. Of course, we can already guess that linear regression runs faster. So with this, we come to the end of this. In the next video, we'll begin to look at some advanced supervised learning models and see how these things go. So let me know how helpful this is for you. And if there's something you'd like me to try out, feel free to let me know. If you have subscribed, thank you for that so much. If you haven't subscribed, please feel free to subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. And you can be a member of my channel to get some special privileges like having a badge displayed next to your name. You can have access to my math PDF notes on based on request, and of course, you can have one-on-one consultation with me, depending on where you belong. Whether you're a bronze, you have bronze access, silver access, or gold access. All right, till I come your way again, keep doing data right. Be sure to like and share so that more people can have access to this great content I have going on here. Bye.